Good day, everyone! This program is for grade 12 students who are studying physical science, but of course, everyone who is willing and interested to learn is welcome to join us. Please make sure that you have a pen and paper with you so you can write the things that you will learn from this episode. In our previous episode, we learned how the elements were formed in extremely hot environment like the early universe, the core of the stars, supernova, and collision of neutron stars. Today, we will discover how the elements are synthesized in the laboratory and how the concept of atomic number led to that. I am Teacher Iman, your host, and I welcome you to the third episode of Science Eskwela TV, where you can learn science concepts in fun and easy way. The periodic table of elements as we know it today has not always looked like that. When I first saw the periodic table of elements as a first-year high school student or a grade 7 student in Pampanga, there were still elements in period 7 that were not yet discovered or synthesized. Symbols like UUT and UUP were used to represent these elements. When Dmitry Mendeleev first arranged the elements in the periodic table in 1869, it looked like this. He left spaces for elements that were not yet discovered. You can also notice that the heaviest element known then was uranium. So much has changed since then. Missing elements were not only discovered, they were also synthesized or made in the laboratory. In today's episode, you will learn the processes by which elements are made in the laboratory, but before that, you first need to understand the essential vocabularies and concepts about atom and nuclear reactions. Let's begin by watching an episode of the game show entitled, Who Wants to Be a Scientist? Ladies and gentlemen, welcome to Who Wants to Be a Scientist? And I'm your host, Manuel Maglasang. Today is a very special episode because our contestant is a teacher from my province, Pampanga. But what makes this episode special is our contestant's favorite subject, science. Let's all welcome Ma'am Leia Andrea Galindez. Good evening, Ma'am Leia.
Good evening, Manuel.
How are you feeling today?
I'm a little bit nervous, but I'm so excited to be here.
We're also excited to have you here. We love having science teachers on the show. So what's going to happen here is really simple. All you have to do is to answer 4 questions. And if you're able to answer all 4 questions correctly, then you will win a science laboratory for your school. So are you ready?
Yes, I'm ready.
If you're ready, let's start with the very first question. Question number 1. What do you call a nucleus that has 2 protons and 2 neutrons but has no electrons? It is usually emitted during a radioactive decay. A. Lithium. B. Alpha particle. C. Hydrogen. Or D. Beta particle.
Let me check. Definitely, it is not hydrogen because hydrogen has 1 proton. And obviously, it is not lithium because lithium has 3 protons. Beta particle is emitted during radioactive decay, but it is not made up of protons or neutrons. It is made up of high-energy electron or a fast-moving electron. So, my answer is letter B. It's the alpha particle because alpha particle has 2 protons but has no electrons.
Letter B, is that your final answer?
Yes, that's my final answer.
Let's see. Her answer is letter B, alpha particle. And it is correct! Good job! Let's now move on to the next question. Question number 2. What does the number 24 in the isotope notation of magnesium-24 refer to? A. Number of neutrons. B. Atomic number. C. Mass number. Or D. Number of magnesium atoms.
I'm sure about this. It's C, mass number.
That was fast. Why is your answer C?
Well, we use the isotope notation to allow us to determine the mass number, the atomic number, and the number of protons and neutrons. So definitely, it is not D. It does not tell us the number of atoms. The number at the bottom, which is 12, tells us the atomic number or the total number of protons. That eliminates B. The number at the top refers to the mass number, which is the total number of neutrons and protons. Through deduction, the mass number can tell us the number of neutrons. For example, magnesium has 12 protons. If the mass number is 24, then 24 minus 12 is equal to 12 neutrons. So yes, the mass number can indirectly tell us the number of neutrons. But 24 here does not refer to the number of neutrons. That makes letter A wrong. My final answer is C, mass number.
Wow, that was very comprehensive. Let's see if your answer is correct. Letter C, mass number. It's correct! Congratulations! Now let's move to the third question. Which type of radioactive decay is represented in the following nuclear reaction? A. Alpha decay. B. Beta decay. C. Positron emission. Or D. Electron capture.
I don't think it is an electron capture because if it is an electron capture, then an electron should have been added to radium. I don't think it's beta decay because if it is beta decay, then the beta particle should have been emitted. And also, it is not a positron emission because if it was, a positron should have been emitted. So my answer is A, alpha decay. As you can see, an alpha particle is emitted. An alpha particle has 2 protons and 2 neutrons, just like the helium, but it does not have electrons.
It seems that you really know what you're talking about. Let's see if you got the correct answer. Letter A, alpha decay. Is correct! Good job! Now let's go to the fourth and final question. Which of the following is not a possible method for synthesizing new elements in the laboratory? A. Neutron capture by nucleus followed by beta decay. B. Direct addition of protons to the nucleus. C. Direct addition of a nuclear projectile that contains 1 or more protons. Or letter D. Mixing chemicals to form new elements.
That's a tough question, Manuel. Okay, for letter A, when nucleus captures or absorbs a neutron, it sometimes makes the nucleus unstable because of too many neutrons compared to protons. This instability results to beta decay, where 1 neutron is converted into proton, and a beta particle, an antineutrino, is released. Now that the nucleus has more protons, new element was synthesized. So, A is not the answer. B is also not the answer because if proton is added into the nucleus, it will become a new element. The same is true with C. When projectiles like deuteron, alpha particle, and other nuclei are added to the nucleus, new elements can be synthesized. Since the question is not a possible method, then my answer is letter D, because mixing new chemicals does not form new elements.
Letter D. Mixing chemicals to form new elements. Is that your final answer?
Yes, that's my final answer.
Let's see. Letter D is correct! Congratulations, Ma'am Leia. You have won your school a new science laboratory. I'm pretty sure your school is very proud of you. Thank you everyone for watching Who Wants to Be a Scientist. Next week, our contestant will be a senior high school student. It could be you. So watch this old video by Professor Nucleon about atoms to help you review for the next episode of Who Wants to Be a Scientist? Good day, everyone. My name is Professor Nucleon, and I am here to talk about the discovery of atom and the concept of atomic number. In 1897, J.J. Thomson was working on cathode ray tubes. In his experiments, he discovered the presence of a negatively charged particle inside an atom. He called them corpuscles, but now we call them electrons. He thought that these negatively charged particles were embedded in a positively charged atom. This was proven wrong when in 1911, Ernest Rutherford did the gold foil experiment. He took a very thin gold foil and bombarded it with alpha particles. He then surrounded it with a screen that can detect alpha particles. He observed that most of the alpha particles passed through the foil. He concluded that most of the atom is empty space. He also observed that some of the alpha particles were deflected sideways and some bounced back. He concluded that the positive charge is concentrated at the center, while the negative charge orbits around it like how planets revolve around the sun. That is how he discovered the nucleus. Back then, they imagined the atom to have a positively charged nucleus with electrons orbiting around it. Soon, Ernest Rutherford discovered that the nucleus of an atom is made up of positively charged subatomic particles called protons. In 1932, James Chadwick, who was a student of Ernest Rutherford, did an experiment with alpha particles and beryllium atom. He fired beryllium with alpha particles. A form of radiation was produced. He observed that this has the same mass as proton but has no charge. He later called these neutrons. We now know what's inside the atom. At the center is a positively charged nucleus where protons and neutrons are found. Orbiting around it are negatively charged electrons. The combined number of protons and neutrons in an element is called the atomic mass or the mass number. When the periodic table was first arranged by Mendeleev, it was arranged according to its atomic mass, even though there were some inconsistencies. For example, if you look at the placement of cobalt and nickel, cobalt was placed first before nickel, even though cobalt had greater mass number. They couldn't switch their places because the properties of cobalt were more similar to rhodium and iridium, and the properties of nickel were more similar to palladium and platinum. All of these confusions were solved when Moseley proved that the major properties of an element are determined by the atomic number. The atomic number of an element refers to the number of protons that element has. For thousands of years before 1600s, the alchemists had been trying to transmute base metals like lead into noble metals like gold. They were unsuccessful because they were just simply mixing chemicals. If they wanted to change the identity of lead, which has an atomic number of 82, they should have taken 3 protons off of the atom. It would have reduced its atomic number into 79. It would have turned into gold. But you can't do that simply through chemical reaction. Atoms need to undergo nuclear reaction. And my colleagues in the future around 20th century discovered nuclear reaction. They used this knowledge to synthesize new elements in the laboratory. A friend of mine from the future, Professor Baryon, will talk about how the new elements were synthesized in the laboratory. I will now bring you to his laboratory. Hi everyone, welcome to my lab. As you may have already known, my name is Professor Baryon, and I'm here to help you understand how new elements are synthesized inside the laboratory. But first, I'd like to show you how the periodic table of elements looked like before World War II. Just like the periodic table that we have today, the elements were arranged according to their atomic number. However, unlike the periodic table that we have now, this one has lots of gaps. Elements number 43, 61, 85, and 87 were missing. Notice also that the heaviest element known then was uranium. I will show you how some of these elements were synthesized in the laboratory. In 1937, 2 Italian scientists, Carlo Perrier and Emilio Segre, discovered element number 43. It was named technetium. The name was derived from the Greek word technetos, which means artificial, because technetium was the first element to be synthesized in the laboratory. What they did was they bombarded molybdenum with deuteron. Deuteron is an isotope of hydrogen that has 1 proton and 1 neutron. When this deuteron hits molybdenum, its proton is attached in the nucleus and neutrons are emitted. The addition of 1 proton into the nucleus of molybdenum turns it into element 43 or technetium. If you look in your module, you will find that the nuclear process that led to the synthesis of element technetium was written this way. The addition sign here indicates that the process involves the combination of deuteron and molybdenum. The numbers on the side can tell us three things. It can tell us the number of protons, the number of neutrons, and the mass number. The number at the top represents the mass number or the total number of protons and neutrons in the element. Molybdenum here has a mass number of 97. This means that if you count all the protons and all the neutrons in this atom, you will count 97. The number at the bottom is the atomic number. This number tells us how many protons there are in the element. This means that molybdenum has 42 protons. If you add one more proton here or take away one proton, it will stop from being molybdenum. Can you tell how many neutrons molybdenum 97 has? Since the total number of protons and neutrons is 97 and the total number of protons is 42, to get the total number of neutrons, all you have to do is to subtract 42 from 97. As you can see from the equation, the combination of deuteron and molybdenum resulted to the formation of technetium and the release of 2 neutrons. One of the missing elements is element number 85. In 1940, Dale Corson, K. Mackenzie, and Emilio Segre discovered the said element. They used a cyclotron to collide alpha particles with bismuth. A cyclotron is a circular machine that accelerates particles or nuclei to collide them with other nuclei. The cyclotron makes sure that the particles are moving fast enough to overcome the electrostatic repulsion between atoms. Alpha particles have protons. Bismuth have protons too. When these two come close to each other, the protons in them will try to repel each other. That is why physicists use cyclotron to make sure that the particles are moving fast enough to overcome this electrostatic repulsion. What they did was they bombarded bismuth with alpha particles. 2 protons from the alpha particle attached to the nucleus of bismuth. The addition of protons changed the identity of the element and it became astatine. 2 neutrons from the alpha particle is emitted. We can also see the process by just looking at the equation. Bismuth and alpha particle were added together. Notice that for alpha particle, we used the symbol He. This is because alpha particle is technically a nucleus of helium. We can also use the Greek letter alpha to symbolize alpha particle. The collision of both resulted to the absorption of 2 protons, which increased the atomic number from 83 to 85, and the emission of 2 neutrons. The other 2 missing elements were discovered as a product of fission of uranium. I also mentioned earlier that the periodic table of elements before the Second World War shows that the heaviest element was uranium. In the early 1940s, physicists Edwin Macmillan and Philip Abelson discovered the very first transuranium element. Transuranium elements are the elements heavier than uranium. In your module, you will see that the process involved in the discovery of element 93 writes as. What do you think happened here? The first part shows that uranium-238 collided and combined with neutron. Uranium now has an additional neutron in its nucleus. You might be wondering why the number of proton increased when no proton was added. This is what actually happened. First, the neutron attached to the uranium nucleus. Second, atoms that have too many neutrons compared to protons have greater tendency to undergo beta decay. When this happens, one neutron turns into a proton, and a beta particle is released. This is the reason why in the equation, it shows that one proton is added instead of a neutron. Element 93 was named Neptunium, named after the planet Neptune, which was the planet after Uranus. If element 92 is uranium and element 93 is Neptunium, what do you think did they name element 94? They named it plutonium. Plutonium was synthesized at the end of 1940 by Seaborg, Macmillan, Kennedy, and Wall. This time, they bombarded uranium with deuterons in a cyclotron. Take a look at these and see if you can figure out what happened. First, uranium was bombarded with deuterons. The proton from the deuteron attaches to the nucleus. This turns uranium into neptunium and 2 neutrons are released. This neptunium-238 is highly unstable. One of the neutrons will turn into a proton. This will turn the number of protons into 94. Element 94 is plutonium. Element 95 was synthesized by neutron capture. 2 neutrons were absorbed by element 94. Then, 1 neutron turns into proton. Elements 96, 97, 98, and 101 were synthesized through alpha particles bombardment in cyclotron. The discovery of element 99 and 100 was interesting. They were found from the debris of a hydrogen bomb explosion. The energy from the blast made neutron capture possible, which resulted to the synthesis of many heavy elements, including element 99 and 100. Elements heavier than element 103 are considered super heavy elements. They are usually produced and synthesized by bombarding heavy nuclear targets with heavy projectiles. For example, the most recently synthesized element is tennessine. It was prepared by the bombardment of berkelium with calcium. The heaviest element known so far is element 118, oganesson. It was made through the bombardment of californium with calcium. If you want to create elements heavier than oganesson, you can try to bombard calcium with einsteinium. But the problem is the scarcity of einsteinium. We are yet to see what new elements will be synthesized in the laboratory. I hope I was able to help you understand how elements are made inside the laboratory, and I will give you back to Teacher Iman now. Thank you, Professor Barian. Today, with the help of Ma'am Leia, Professor Nucleon, and Professor Barian, we learned about synthesis of elements in the laboratory. You have learned about some important nuclear processes like alpha decay and beta decay. You have also learned about atoms and the concept of atomic number. Lastly, you have learned how new elements are synthesized in the laboratory through the capture and absorption of neutrons. You also saw that it is possible to synthesize new elements through the addition of protons to the nucleus and the addition of a nuclear projectile to the nucleus. Before we end this episode, I'd like to share something that I hope will encourage you. Change is the only thing that is permanent. For many years, people believed that everything was made up of 4 elements. Then it was proven wrong. For a few decades, many elements in the periodic table were missing and undiscovered. But now, all 7 periods have already been completed. Right now, the pandemic seems to have no end in sight. Take comfort in knowing that change is the only thing that is permanent, and this too shall pass. And speaking of change, next week, new lesson and a new teacher. You've already met her. Let's welcome Teacher Leia.
Hi, Teacher Iman.
Hi, Teacher Leia, and welcome to Science Eskwela.
Thank you, and I'm so excited to join our senior high school students as we learn physical science. Join me on the next episode as we learn about the polarity of molecules.
And that's it for this episode of Science Eskwela. Don't forget to tune in on our next episode because learning science with Teacher Iman
And Teacher Leia
is fun!